Okay, so I'd like to acknowledge two collaborators that were very helpful in pulling this talk together. One is Dr. Danielle Wayne, who's the new Lake Science Director at the Seven Lakes Alliance, and also Charlie Bader, who was the project manager for the East Pond Alum Edition, and they both work for the Seven Lakes Alliance. So this talk is really a collaboration between my group at Colby and the Seven Lakes Alliance. So how did the lake go bankrupt? Maggie sort of highlighted this, two ways, gradually and then suddenly. And this is an image of East Pond that's still on the Microsoft Bing image. It's rolled off of Google. But you can, I always ask my students, which lake would you buy property on? Right? And they would always pick North Pond because they can see from this aerial photo that North Pond, when this image was taken, is clear and East Pond was visibly green. So this is the challenge that we were trying to solve. And the good news is because of the long-standing volunteer commitment in the state of Maine, we actually have really good water quality, fairly good basic water quality for many of the lakes in Maine, including East Pond. And this is the Secchi transparency in East Pond since it was collection was started in the early 70s. And you can see that there was a fairly dramatic shift in the transparency. So, up here at 1 meter is pretty bad. That's what it looks like with a Secchi transparency of 1 meter, and 7 is really good. And there was clearly something that happened right around the 80s where there was this, rapid change, and that's really the cautionary tale for many of us, is that the lakes can appear to be in good condition, and then all of a sudden you get this sort of change, and that can be driven by a defining storm, which is probably the case in East Pond, or you can just sort of cross a threshold, and then you're in a new ecological state. And that's what we really are worried about. And once you cross into that ecological state, that new condition, you got to pull it back somehow. So what I'm going to do today is I'm going to tell you how we pulled back East Pond, and hopefully how we've reestablished a clean water system, and some of the levers and decisions that we had to make. Let me just back up and say, this is all of the data for East Pond. When we plot it on an annual basis, we get something that looks more like this. So this is the spring, this is Secchi depth, and this is 2 years. This is 2016 and 2017. And you can see that the average Secchi doesn't tell you a lot. It's really the profile of the Secchi over the course of the season that's helpful. So we have a spring bloom that's dominated mostly by golden and green algae. Then they run out of phosphorus, and they run out of nitrogen, and the lake gets clear. And this is the sort of classic clear water phase. But what happens on East Pond, almost like clockwork, is bam, the lake used to bloom right around August 6th. And we could actually predict this about 5 or 6 days before it's going to happen. I could call up Jerry Tipper on East Pond and say, you got about 6 days, and it's going to bloom, and sure enough, it would bloom, and then this is what it would look like. So if you're just looking at the average Secchi, you might, if you average these numbers, you're going to be sort of here. It doesn't look so bad, 3.5 to 4. It's really the profile of the Secchi. So as a lake association, one of the things I would like all of you to do is look at your data, look at it every year, plot it different ways, and don't forget the shoulder seasons, okay? The lakes don't operate from Memorial Day to Labor Day, okay? Put your boats in early, take your boats out late. Pete Callan keeps sending us data from like November on Long Pond. That's really helpful. And it's really important. So just to reinforce that point, if we plot the average Secchi on Great Pond for all of the years that we have data, things have declined from 4.9 meters to 3.3 meters. But if you plot the minimum Secchi, you get something that looks like this, okay? That's the minimum Secchi, and this is the bloom condition, right? So nobody gets out in a lake that looks like this and says, yeah, water quality's good. The average Secchi's 3 meters this summer. You get in this and you're like, this is gross. it's August, and you've lost the entire season, essentially, because of those blooms. So really important to pay attention to your data and put it into the context of how people are interacting with the lake. And Maggie talked about fear. Yeah, you show that slide a few times, and it gets people's attention. Okay. So today what I want to do is take you through a timeline of what happened on East Pond and how we got involved and how our thinking evolved and how it finally ended up to what happened in 2018. So let's see, the first recorded bloom on East Pond happened in 1976. I got to Colby in 1989, so I'm one of the old folks still hanging around on campus. And then a couple of really good things happened. The National Science Foundation paid for a self-propelled sampling platform in 2001. Don't ask NSF for a party boat. Ask them for a sampling platform and then put all kinds of instrumentation on it, and that's what we did. And then when I moved to Waterville, I bought a house in Waterville from Betsy and Jerry Tipper, because they were moving to East Pond to build their retirement home. Well, it turns out that was a good introduction, and then it turns out Jerry went to grad school with my dad, and he dated my aunt, and it's like, so all of a sudden there was this connection to East Pond, and so I get these phone calls, hey Whitney, come out to East Pond, I want to introduce you to East Pond. The relationship between people and the academic was really clear, and I had this boat, and he let us park our boat in front of his camp and use his facilities and his docks and his skiffs and everything else, and so that really got things going. And then we had this really cool boat. And that's the other second lesson, is don't be complacent with the status quo of the sampling that you're doing and the procedures you're using. Science has developed a whole bunch of new sampling, everything from the hobo sensors that measure temperature to better oxygen and temperature sensors, to some of the new DNA testing that Pete Countway is going to talk about later this afternoon. Those are all really important tools. And this is a GPS with depth and chart plotter capability. And those are really important because they map depth as you drive around the lake. Garmin makes a number of good ones. Lowrance makes some good ones. And all of these enabled us to do better lake science than we could using sort of the traditional techniques. So one of the first things we did is we went around the Belgrades, and I paid 2 students for the summer to map the depths of all the Belgrades. So their job was to get in this boat and drive up and down the lake, over all the lakes, and it took them all summer in 7 propellers. Right, because you don't want to stay in the deep part, right? So 7 propellers later, we had about 1 million data points. We contoured the lakes, and we had these great maps of the lakes. And so that's sort of fundamental knowledge. So if your lake doesn't have a good bathymetric map, go make one. Because now what this map allows you to do is to understand what is the shape of the lake. How deep is the lake? Where would you treat the lake? So this is East Pond. It's around 1,700 acres, and we can now have a virtual transect. If we went from the south to the north, this is what the bottom of the lake looks like. So the lake, East Pond, is a bathtub. Now, Great Pond is kind of like a margarita glass, and other lakes have different profiles, and it's really important to understand that. The other thing is, as we started this work, everyone said East Pond's well mixed, uniform temperature top to bottom, uniform oxygen top to bottom. And then we went out with our new sensors and we made those measurements, and this is a heat map. So hot is red, cold is blue, and East Pond was not uniform top to bottom. East Pond is stratified for at least 4 to 6 weeks a year. And that actually was a game changer, and it started to get us thinking about what's going on in East Pond and what does this mean when you have this thermocline that forms for at least a couple of weeks every summer. Okay, so now we know something about the Belgrades because we spent a lot of time mapping them. East Pond is right here. It's the headwater of the Belgrade chain. Water flows from East Pond into North Pond, into Great Pond, into Long Pond, and then finally out, and Colby is somewhere over here. So it's a great place for us to work, but it's also this interconnected chain of lakes. And because we had all the bathymetry, we know its area. Well, that's easy. You can get that off of Google now. But we also know its max depth, its mean depth, its watershed area to flushing rate. And we know the residence time is on the order of 2.5 years. I actually think we're going to be able to improve that number, and I'll try to mention that at the end of the talk. 2.5 years is important because it means that something I do to the lake this year is going to be there next year, right? So this is, right, because it takes, yeah.
Is that the same as flush rate?
Yes, it's think of it as the length of time it takes to fill the lake. 2.5 years, right? Like, so flushing rate. So the flushing is probably the reciprocal of this, but you get the idea. So that means that water in the lake hangs out for about 2.5 years. So that means you're connecting multiple years together. And of course, we also have all sorts of images of green water quality in East Pond, and of course that's the problem that we're trying to solve. Okay, so the NSF got us started on this, and then we did this work on the bathymetry, and we started to couple that bathymetry to physical models of the lake. So the Global Lakes Observing Network, which is a collaboration of academic lake researchers from all over the world, has developed really good models for how lakes mix, and they're calibrated models, and you can actually build those on your lake. So Danielle Wayne at the Seven Lakes Alliance is getting the R code up and running so that you could actually do that on your lake. And the advantage of the models is they don't always tell you the right answer, but they let you test scenarios. And so what would happen if it was a bit warmer or a bit rainier, and what would we expect, how would we expect our lake to change? So we started to build these physical models, and the models taught us something about the lake, and I'll show you that in a minute. In 2005, the DEP was sufficiently alarmed with the water quality on East Pond that they approved a perch removal, and the idea of the perch removal is they were going to biomanipulate the lake. The perch eat zooplankton, and the zooplankton eat phytoplankton. So if you took out the perch, the zooplankton would grow, and they'd take out the plankton that was blooming. That was the idea. We weren't involved in the specifics of the perch removal, but we were involved in trying to understand the dynamics of the lake. And so during that time, we started putting in high-resolution temperature measurements, and that turned out to be really helpful. So let's look at that. What we did is we put a cinder block at the bottom of the lake, put a buoy at the top, and we put thermistors, so a temperature-sensitive resistor that can measure temperature, and they're cheap. They're about, you can buy them from a number of different vendors, but they cost about $60 a piece. We stuck them in the lake, and we left them out for the whole summer. So instead of going out once every week or every 2 weeks and making a few measurements, we picked one spot and we measured the temperature every 10 minutes for the entire summer. So now you have a lot of data, and you could start to ask questions about how does the lake mix, because temperature tells you a lot about what warm water floats and cold water sinks. And this is what we observed in 2006. So the blue line is the bottom of the lake, and the gold line is the top of the lake. And when the two are the same, the water's mixing. And when there's a difference in temperature, the water's stratified, and you have a thermocline. And you can look at the differences between these lines, and this is red. Red is cut off 6.5 meters. So we had a thermocline between 5 and 6 meters. So what do we have? We have the lake warming up. The bottom water was warming up, but the surface water was warming up faster. And then right around the end of July, bam, stopped. The surface water cooled down, the bottom water stayed the same temperature. This is the cool August nights. In August, the sun is now, the daylight shorter. You get these clear August evenings, 50 degrees. We all know this when we go out to camp, and we get radiative cooling from the lake, and the surface water cooled down, and when the surface water cooled down to the bottom water, it mixed. And then it mixed all the way through the fall. The beauty of this is we measured the 6 different lead depths every 10 minutes, all summer long, and we get this beautiful record. Okay, and this just shows you a blow up of that, right? Day 220, the lake mixed. So East Pond is not a well-mixed lake. not well mixed for the month of July, but it does become mixed in August. So this was really important in trying to understand what was going on in the lake. Okay, so taking that data and our physical models and our numerical models, we can start to put together a cartoon of what actually is happening on East Pond. And in the beginning of the year, let's say May, the lake is well mixed. And that's because it's warming up, there's enough wind, the lake is mixed well, and some periods of the summer, that's also true. But it's not always well mixed, and we have ephemeral, temporary stratification during the calm, warm weather, starting sort of like today, and hopefully extending for, the next 6 weeks. So, temperature's warmer at the surface, you had a thermocline. This is just about the shape of East Pond, so that's about right. That temperature creates a barrier for mixing. That barrier for mixing means that the oxygen isn't being replenished in the bottom of the lake, and the dissolved oxygen concentration goes down. Okay, that's because of respiration primarily of the sediments. Okay, so it's not fish, it's not sort of plankton in the bottom of the lake, it's organic material acting like a compost pile, a big lake-wide compost pile, and it's sucking the oxygen out of the bottom of the water, and there's no way to replenish it because we have this thermocline. Okay, so now that we've depleted the oxygen concentration goes down, that releases phosphorus from the sediment. We'll talk about how that happens in a minute. And we have phosphorus released. Good news is that phosphorus right now is still stuck at the bottom of the lake because if oxygen can't mix down, phosphorus can't mix up. Okay, so we had phosphorus building up. How do we know? Because we took samples of phosphorus at the bottom of the lake. Second lesson to lake associations is don't always assume you're going to measure every meter in the lake. All the action on East Pond happens in the bottom half meter of the lake. So if we only measured in 1 meter intervals, we would have missed all the chemistry and the story on East Pond. Shallow lakes should be sampled more frequently, vertically. Deeper lakes you could stick to 1 meter, but in something like East Pond, I would say you certainly near the bottom, you want to be measuring every 10 centimeters and maybe every half a meter because that's where the action is. Don't miss the action by just sticking to the script. Okay, so then what happens is right around August 1st, the lake starts to cool, and you have a wind event often that sort of sets this up, and that cool nights and warm wind causes mixing in the lake. The lake mixes, the phosphorus that was all down here is now everywhere in the lake. The water's still quite warm, and you get a bloom. Okay, the bloom is not the generic, it's not the general portfolio of plankton. The bloom that happens in August tends to be anabina, because anabina is capable of using that phosphorus fairly effectively, and they fix nitrogen from the atmosphere. So this mechanism doesn't put a lot of nitrogen back in the lake, but it puts phosphorus in the lake. And the anabina, at least in East Pond, are able to take advantage of that. So we get the bloom that I showed you early on. Okay, the problem is that this amplifies itself. Because we put a bloom up high in the lake, the sunlight is absorbed high up in the lake, and if you absorb the sunlight, the surface warms, and if you warm the surface, you reinforce the thermocline, and because you reinforce the thermocline, you now have even less oxygen in the bottom of the lake, and this happens 2 or 3 times over the course of the summer. So you get this sort of negative feedback that drives the plankton beast at the top of the lake. So this cycle keeps repeating, pumping phosphorus into the lake. Now this happens because in East Pond because of the specific depth. And different lakes at different depths will either mix more frequently or less frequently, and as lakes get deeper, they tend to only mix in the fall. That's good, because then the plankton, if the bloom happens, would happen later in the season when everyone's gone home, unless they have a residence time that's 2 or 3 years, in which case that phosphorus is in the surface and then mixes, and it's waiting for you next spring, and it helps reinforce the bloom. So there's lots of dynamics that you need to keep in mind. Okay, so at the end of the summer, the algae that bloomed in East Pond dies, and what does it do? It builds the compost pile for the next year. Okay? If you dive to the bottom of East Pond, I can stick my arm right up to my shoulder in the muck, and that muck is about 25% organic carbon. I mean, there is a compost pile at the bottom of East Pond that is humongous, and that is always a source of oxygen. And one of the best ways to monitor that is to actually sample through the ice in the winter. So that's another lesson to the lake associations. Ice sampling is really important. Go out there, drill a hole, take an oxygen profile. If you're losing oxygen in the winter, it tells you a lot about how fast the oxygen is being taken out of the lake. That's another really good thing to do. All right, so residence time in the lake is 2.5 years, right? So this process is sort of evolving, developing over a decade, and nutrient buildup can amplify over several years, and that's certainly what was happening in East Pond. Okay, so as we're moving along in this collaborative journey, we learned this really, in 2005, 2006, and then around 2010, a really good thing happened to the lakes in Maine. The National Science Foundation gives pork money to poor states with bad science programs. It's called the Experimental Program to Stimulate Competitive Research. It's designed to build the science infrastructure of states with weak science infrastructure, and Maine is one of those states. And they give us about $20 million. It's a competitive process, but Maine's been fortunate to get about $20 million every 5 years for a really significant scientific program. And what was funded in 2010 was the Sustainability Solutions Initiative, which was really looking at coupled natural systems. So this is a lot what Maggie was talking about. How do people interact with the natural environment? And it was really helpful in us to study the effectiveness of Lake Smart and the barriers for people adopting Lake Smart. It also gave us a lot of funding to study the lakes in more detail. So I don't think the work we're going to describe in a minute would have ever been possible if it weren't for the Sustainability Solutions Initiative. So your tax dollars are actually paying dividends in this case. The other thing that happened in 2011 is that we built the Maine Lakes Resource Center in downtown Belgrade. And so this is an amazing building with access to the water and venues and a place for my students and others to do research right next to the lake. And so that's been a great addition. And so that is the home of the Maine Lakes Society and conservation organizations. The Belgrade Regional Conservation Alliance was there, and now that's merged with the MLRC to become the Seven Lakes Alliance. So that was a really good thing for the research in the Belgrades. Okay, so what happened as part of a lot of this sustainability work is that we had a number of meetings with the community, and what we're hearing from the community was, would you stop studying the lake and just fix it? My favorite one is I got a phone call from someone in East Pond, and I don't remember who it was. They called me, got me in my office, and they said, we heard you're working on East Pond. My daughters could be married in 2 weeks. Are you going to have it fixed in time? And I was like, whoa, thanks for the endorsement, but no, that might take a little bit longer. But anyway, there was this attitude about moving from studying the problem to coming to solutions. And the community was very engaged in developing those solutions. And at about that time, Ken Wagner got involved. And Ken Wagner is one of the country's top limnologists and is very involved in lake restoration. And his company's based in Boston. He loves to come to Maine. And he was a great collaborator in thinking about the solutions, the engineered solutions. We had a pretty good handle of what was happening sort of fundamentally from a science standpoint in the lake, but what he had was experience in actually treating lakes and doing it with a whole range of different remediation strategies. So one of the first things Ken did is, okay, let's create some budgets, let's figure out how big a problem we have, and the first one is water. Right? So you're gonna have a lake, you gotta know what the budgets are. And so what do we have? We have about 5 million meters cubed of water coming off of the streams. We have about 7.5 million meters cubed coming in from the atmosphere. We know the volume of the lake. The geese don't contribute any water. And so we actually knew something about the lake, and we had a little bit of groundwater coming in. Now, if you take the phosphorus concentration in these average flows, you can turn the water flows into nutrient flows. And so we did that. And this is really helpful. The watershed was contributing about 200 kilograms per year. So that's, you don't need a pickup truck for that, Maggie. You just need like a, SUV. Okay. And then internal load was 400, right? So the internal load was 4 times the watershed load. Twice, thank you. And that's in part because the East Pond Association had been working with people around the lake to try to decrease their watershed runoff. Wildlife gives a little bit, and then you get a little bit of atmospheric deposition, but you can see that the internal load coming from the sediments was calculated to be big. So you got to know that, because if you're going to have a solution, you better figure out how big the problem is and whether your solution is going to have any effect. So you turn that into a pie graph. Half the water comes from the atmosphere, half comes from runoff, but half of the phosphorus comes from the sediments, and the other half is divided between groundwater and, surface water and atmosphere. So this was the piece of this pie that we could manage. Turns out it's a lot easier to treat the internal load than it is to treat the watershed load, because if everybody did something right, you might be able to cut this piece in half, but if you immobilize all of the phosphorus, you might be able to cut this piece by 60 or 70%. So you got to understand that, what you can do. Okay, so we decided to tackle this piece. And we tried other things. We tried to reduce the external load, and yeah, that was moderately successful, but again, that piece of the pie is just not that big. They tried the biomanipulation. They couldn't remove enough perch to substantially change the zooplankton population, and it turned out the zooplankton don't like Anavina, so they weren't going to eat it anyway. And so it was a great thing to try, I guess unless you're a perch, but it was, it didn't work. Okay, so we need something else. Okay, so what we decided on was aluminum, alum. And so it's a chemical treatment. I'll show you. It's a really big chemical treatment. And what we're going to do is we're going to add naturally occurring compounds, iron and aluminum, and both of them are really good at binding phosphorus. So I'm a chemist. This is the only chemistry slide. Well, maybe there's a couple more. But this is iron oxide. This is rust. Rust is really good at binding phosphorus. This is aluminum oxide. It's the gray stuff you see on aluminum pipes. It's also really good at binding phosphorus. And so if you add these solids to the lake, it binds them up and it removes this. We know a lot about this chemistry because this is what happens in your drinking water. So the China Lake Water District, the China Lake, the Kennebec, I gotta get this right. Kennebec Water District, which is the water I drink in Waterville, runs through a bed of aluminum to remove the stuff that's in China Lake before I drink it. And it's also used in wastewater treatment. Okay, so aluminum and iron are both used, but they're not equally effective, and it depends on the context in which they work. So I'm going to give you a diagram. This is a roadmap for why or why not iron's effective. So these are different chemical forms of iron. So this is iron 2, this is iron 3 oxide. This is what binds phosphorus. This does not bind phosphorus. And this is pH, very acidic, very basic. Lakes are right about here. This axis is electron concentration. So this is an oxygenated lake, and this is an anoxic lake. So I can move around this diagram, and it tells me which chemical form of iron is dominant. All right, so in a lake that's got lots of oxygen in it, at pH around 7.5, which is where most of our lakes are, that's where we are on the diagram, and that says iron oxide is the stable form. It'll bind phosphorus. But when you take the oxygen out of the lake goes anoxic, and when you do that, you go to here. So now all of a sudden, the chemistry of the iron's changed. It's iron 2, not iron oxide. You dissolve the rust. That's how you get the rust out of your toilet bowl. Okay? And iron does not bind phosphorus. So what would happen? If iron is what you're using to treat the lake, and it goes anoxic, it releases a lot of phosphorus. So let's go look at aluminum. Aluminum's delightfully boring. It only has really one stable form from pH 3 to pH 12, and at any concentration of oxygen. That's an oxic lake, that's an anoxic lake. Aluminum 3 stays aluminum 3, no matter what you do to it. So you want to bind phosphorus, you want aluminum, not iron. That's why they call them alum treatments. Okay. Now, it turns out that this occurs in nature if you go out and you study a whole range of lakes, and some lakes, sediments of the lakes release a lot of phosphorus and some don't. And the question that Roy Bouchard actually asked at DEP was, why are some lakes releasing a lot of phosphorus and others not? And so Ari Mir-Baumann and Steve Norton at UMaine took on this problem. They collaborated with a couple Czech scientists, and they studied the phosphorus release in a whole range of lake sediments. So this axis is the amount of phosphorus that's released, and this axis is the aluminum to iron ratio of the naturally occurring sediments. So remember, if you go anoxic, iron will release phosphorus, but aluminum won't. So the more aluminum you have, the better it holds on to phosphorus. So out here at 10 times, a 10 to 1 ratio of aluminum to iron, it never releases phosphorus. You come along, and all of a sudden you hit a point at about a 1 to 1 ratio where the phosphorus goes screaming up. Well, 3 to 1, aluminum to iron, is kind of the magic number where this inflection point happens. And East Pond's right there.
Oh.
Okay, so no surprise that the lake would go anoxic and it would pump out a lot of phosphorus. If you looked at the sediments at the top of East Pond, they were red. There was so much iron in the top that it was visibly red. And so what we needed to do was to pull it back and add aluminum to try to restore that balance. So that's what we did. So we then, sort of understanding the chemistry of the lake and the bathymetry and the models, we then looked, okay, if we're going to add alum, how much do we need to add? So we went into the lab. I had a couple of students. They spent an entire month of January doing these experiments. They took some lake sediment. They brought it in the lab. They added a dilute ammonia buffer with oxygen in it. That simulates mixing the sediment with lake water. And they collected the amount of phosphorus that was released, and they analyzed that. Then they took the sediment and they added sodium dithionate. This makes the water anoxic. It simulates the anoxic conditions, and they looked at how much phosphorus was released, and they analyzed that. And they did this over and over and over again for lake sediments as they changed the amount of aluminum that was in the system. They simulated what would happen if you added aluminum to the lake. So I'll show you what their data looked like. These are called jar tests because you do them in jars. Okay, so this is sediment in various beakers, and then what they would do is no aluminum, a little bit more, a little bit more, and a little bit more. And I'm going to show you the phosphorus that came out of these sediments versus the aluminum dose, and I'm going to show you two treatments: the oxic water, that's sort of regular lake water with plenty of oxygen in it, and then the anoxic water, which is lake water with no oxygen. So if you don't add any aluminum, you get a big difference. This is the anoxic water, a lot of phosphorus release. This is the oxic water. This is kind of our reference point. And then what they did is they increased the dose of aluminum, and as you added more aluminum, it holds on to the phosphorus. That decreased. All right, this gap is getting narrower. You add more aluminum, it gets narrower. You add more aluminum, it gets narrower. And there's this sort of asymptote that you reach, and we picked it right here. Okay, so this was the point where we add enough aluminum, doesn't matter if the sediment's oxic or anoxic, we get about the same amount of phosphorus released. And so that was the dose that we figured we needed to do for East Pond. And it turned out to be 45 grams per meter squared of sediment. So, knowing that, and I told this was a freshman and a junior. They said, yeah, you guys had a productive January. You just set a $1.1 million budget. That's kind of a fun thing to do. All right, so if you know the dose, and you know the lake area, and you know the price of aluminum, and that was the wild card in this whole treatment. We knew the first two really well, but the price of aluminum fluctuates. You could set the cost for this project. All right, so 45 grams per meter squared. We had to treat 676 acres. That meant 136 tons of aluminum. That meant if we delivered it as a liquid, some 500,000 gallons. You get an idea, this is not messing in the lab. This is serious industrial chemistry. That takes 82 tank trucks, 82 18-wheelers to do this. Okay, so at that point, I don't have to sequence it quite right, but to implement this, you can't just go out and say, hey, we're going to go dump 82 tank trucks of aluminum into East Pond. There was actually a steering committee that consisted of the East Pond Association, my group, Ken Wagner, the towns of Oakland and Smithfield, which is where the lake exists, the camp owners, the soil district, consultants, and et cetera. All got together, and then the permits came from DEP. Okay, so you have to get a permit to do this. And there were subcommittees to looking at the science and the fundraising and the communications. So the community really got involved in the implementation. Fundraising, this is $1 million project, so you got to raise the money. So the costs, the aluminum cost was about $1 million. We had to put a road in for those trucks. Ken Wagner wanted to get paid. Some of the Seven Lakes expenses need to be covered, monitoring, interest, about $1.1 million. So my salary's not in there, my student salary's not in there, the boat's not in there. If you were going to do this without an academic partner who gets paid through other ways, this project would probably cost closer to $2 to $3 million. Just so if anyone's thinking about this, partnerships are good, particularly if somebody else is paying your partners. So to do this, Jerry Tipper not only provided the dock for the boat, but he also was an incredibly effective fundraiser. He raised about $500,000 in 6 months. That's a pretty good thing. The US EPA gave $200,000 toward this. The Harold Alfond Foundation, where would we be in Maine without the Harold Alfond Foundation, contributed some money. At that point, had the money to sort of make all this work. The Seven Lakes Alliance actually mortgaged their building to cover the loan to do this, right? So there's a really helpful collaborative work here. And then we did it in 2 phases, June 2018 and October 2018, because we needed to get out on the lake when the summer camps weren't in session. They didn't give us the space to get on it, and they didn't want their campers to see those tank trucks rolling through the middle of camp. Okay, so what does this look like? So first thing is aluminum is not soluble at pH 7. And we want to deliver it as a liquid because it's a lot easier to pump liquids than it is to spread solids. So we delivered the aluminum in 2 forms. And if you think this is small, this is the tanks. And we went through those tanks every day. That's a pickup truck back there. We've been playing with pickup trucks here, right? So there we go. That's a pickup truck. It's aluminum sulfate dissolved in sulfuric acid. Okay? And then you can't just dump sulfuric acid in the lake, so you got to neutralize it. Well, we did dump sulfuric acid in the lake, but we neutralized it with sodium hydroxide. And so we had a whole other set of tanks with aluminum dissolved in base. So we have acid, we have base. This is all of the tanks lined up. You would fill the barge up. Just so you know what we're talking about. This solution in this tank has the viscosity of maple syrup. It is at pH between 0.2 and 1. This is really acidic stuff. It's about 7%, 6.5% aluminum. That's the acid side. The base had a pH of 14 and had about 20% aluminum, so we needed a little bit more of the acid than the base. So it was really interesting. They were really careful not to spill any of this stuff on the ground because it might get into the lake, which is kind of ironic. Because that's exactly what we did. All right. So the big tank was acid, the little tank was base. This is the barge they used. Okay, and then they had 2 bars that ran behind the barge, and they literally pumped the chemical out through the bars, and they carefully metered it because they had to deliver it at exactly about a 2.0 to 1 ratio. Because if you got it off, you either acidified the lake and killed everything, or made the pH too high and killed everything. And they didn't kill anything. I mean, there were no fish mortality, there was no bird mortality. They were really, really careful at metering this out. And this is why you got to go with an industrial contractor to do this work. So there they are, running down the lake. He kept saying, we're not adding chemicals. We're restoring nature's balance. Whole conversation we could have on messaging here. Not adding chemicals, yeah. This is what it looks like from the air. You can see the plume. This is the aluminum oxide. This is the insoluble aluminum forming right there behind the barge.
Wow.
Okay, and that's us. Our job was to sniff the back end of the barge and make sure the pH was right, make sure the aluminum concentrations were right, make sure that they measure the plankton. We were the chase boat, essentially, for this project to ensure regulatory compliance in the aluminum addition. I got some more pictures. This is their path. They had to carefully document where they went. They divided the lake up into areas. They would do 2 areas a day, so they'd like do R and then they'd do C. So they distributed the aluminum addition over the whole lake, and they would pick the area depending on the wind and where they've been before. So this is their actual cruise track. You can't see the individual tracks because they're every 40 feet. And they used an agricultural GPS that they used to spread fertilizer. That's the GPS they used to add the aluminum. There's a little irony there, too. Right? And in the second half of the deployment, this is the biggest alum addition ever done in New England. They actually bought a new boat, and this is the new boat. So this holds 3 tanks, two of the acid and 1 of the base, and it can add the aluminum about twice as fast, which saves them a lot of money. This was us. Okay, this is Ken Wagner. If you don't know Ken, that's Ken Wagner. We had computers, we had GPS, we had all sorts of stuff, and we were chasing this boat around. And my students said it didn't matter if it was raining or anything else. It was, a lot of kind of cold, rainy days. This is what the plumes start to look like, and we're chasing back and forth. There's so much particulate form when you do this that it looks like a whale underneath the boat. This is the sonar, if you've ever watched your fish finder from the top all the way down. You could actually watch the plume settle to the bottom of the lake. And we did that, and we took a lot of video of it settling as well. This is what it looks like from above. If you do this, get a drone out there. There we go. And this is us following around in the plume. Okay, this is not a drunk barge driver. This is the bathymetry of the lake, right? So you got to have that bathymetry because he treated everything deeper than 5 meters. And this is the 5-meter line, and this line was deployed 20 minutes before this line. So you really get a sense of how fast the aluminum comes out of the water column and hits the sediment. And that's us. Right? So this was a pretty high shot. Okay. So, alum, better living through chemistry, question mark. I'm probably a spokesperson for Monsanto or DuPont right now. But how did it do? Well, this is 2017. This was the year before the treatment. This is a heat map of temperature. Cold, warms up. There's some stratification that occurs right in here, and then it cools down again. So that's the temperature profile. The little Secchi symbols are the actual Secchi disk, Secchi depth. In 2007, so we had a spring bloom, we had a clear water phase, and then the Secchi got to about 1.8 meters, and it stayed that way for the whole fall. So that was the problem we were trying to solve. This is 2018. We added aluminum right there. We got a spring bloom. We had a really good spring bloom last year. We added aluminum, Secchi went down, 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 and it stayed at 5 meters all summer. Okay? They said the water seemed sparkly. So I think they confused aluminum cans and alum, but okay, the water quality was significantly better. This is the ephemeral anoxic events occurring in 2017. We saw no anoxia in 2018. These are the phosphorus concentrations in 2016 and 2017. Roy Bouchard gives a good reference. He says, 15 parts per billion is when a lake starts to bloom. And there's 15, and in East Pond we were above 15 parts per billion most of the summer, and sure enough it bloomed. There's a whole lot of data on here, but this is all the Secchi measurements, 15, 16, 17, and 18. And 15, 16, 17, they all did this clear water, and then there they all are, blooming. And this is 18, and these points are this year, okay? The clearest spring conditions that we've seen ever on East Pond.
That's so good.
And then the yellow is the phosphorus concentration last summer. And you can see the phosphorus concentration. That's my alarm telling me I'm almost done. So the yellow were the phosphorus concentrations, and they are significantly lower, which makes sense. Less phosphorus, no bloom. Okay, so we got the phosphorus concentration down about 10 parts per billion, and it looks like that decreased phosphorus concentration has persisted throughout the winter and is currently at around 7 or 8 parts per billion right now in East Pond. So again, we know what the condition was through the winter because we made a point of going out. That was the royal we, that was Danielle and a bunch of students, to sample through the ice and collect nutrient and temperature and oxygen profiles. The other thing that happened is that the community structure fundamentally changed in the lake. This is a plot of different plankton. We really only started sampling in the end of July last year, 2017, but we saw almost 100% blue-green algae in East Pond. And in 2018, we had a much better sampling protocol. Before the alum addition, we saw golden and green algae. We went through that clear water phase, and it stayed clear. And there were few blue-greens at the end of the summer, but very few. So we knocked the plankton population down by about a factor of 10. Okay, so there's, we knocked the plankton population down by a factor of 10. We fundamentally changed the ecology of the lake. We engineered it to a new condition, and you have to decide whether that's working. The people that live on the lake are thrilled, but this isn't something to be taken lightly. I mean, if we said that we took a forested plot and removed 90% of the trees, people go crazy, right? That's what we did. We took out 90% of the plankton in doing this treatment. How long will it last? We don't know. It's still a bit of a black art. The science on longevity is still uncertain, in part because many of the other treatments weren't as carefully documented, so it's really hard to know what was the starting condition. So there's really a need for experienced people to be involved in this. The East Pond treatment probably will last 10 to 15 years. The data in the second year is very indicative of the longevity of the treatment, and so far so good. We added enough aluminum to treat the top 10 centimeters of the sediment because that's the depth of bioturbation. If you add more aluminum, you build yourself a little bit of a buffer, but it costs money. And so I think we hit a good compromise between treatment effectiveness and longevity. And then the wild card is the Lake Smart piece, right? How well do property owners do at B&Ps? Because they're really going to determine whether this is a 15-year treatment or a 30-year treatment. And so there's an opportunity to really get people to think about how their impact can sustain their investment, right? $500,000 from the people around the lake. They have some skin in the game. And if somebody next door is throwing dog poop in the lake, they're not going to be very amused, right? So that's important. So this is the largest treatment in New England ever. So we can learn a lot from this East Pond treatment. But if we do this on other lakes, the scale could double or triple. And so one of the things we have to ask is that something that we are willing and able to do? So in summary, East Pond has suffered from algae blooms for over 2 decades. The historic input of P was probably agricultural, but then it was reinforced by camp owners, and there just simply wasn't a mechanism to remove it. It accumulated in the sediments, and it kept coming out every year through internal load. So despite intensive watershed work and manipulation, East Pond continued to bloom. We needed a different solution. We decided that aluminum was the solution, and it worked. It was a quick fix. We actually did something, cost a lot of money, and at the end we should ask, just because we can treat doesn't mean we should. And this is something that as lake associations, everyone's got to wrestle with. Is this something we should do? Because it takes the pressure off, right? That's not so scary if you just, put $3,000 in the kitty and everyone does it, and the boats show up and they add aluminum and the problem goes away. So we have to be careful about what we propose. So with that, I want to make some acknowledgments. let's see.
That beautiful.
Abby and Guillermo were key in doing a lot of the alum additions. Probably had about 25 students involved in this. We had a whole crew working on the project. Ken Wagner was invaluable in the engineering approaches to alum, and he's also just a really nice and engaging guy. Tremendous working with our students. He was out there teaching them all sorts of stuff. It was really fun. Betsy and Jerry Tipper, they let us take over their dock, and they left the doors open to their camp so we could use the bathroom, all sorts of really important things. 150 private donors on the East Pond, the US EPA, Maine DEP, and the Harold Alfond Foundation. So, with that, I'd be happy to take a few questions.
Awesome.